Okay, so for Physics 10, our next section was on vibrations and waves right here, on particularly waves right here. And we might say, what is a wave right here? Now, I don't mean one of these right here. I mean, most waves are some sort of a disturbance that disturbs its neighbor, that disturbs its neighbor. It's a propagating disturbance. If we look at something like ocean waves right here, here's the ocean waves right here. Here, if I were to put a little piece of wood in the water right here and let this wave go by, this wood doesn't go along with the wave, it just bobs up and down. So all you have is disturbance here, and that disturbs the neighbor, disturbs the neighbor, disturbs the neighbor, and it just propagates down right here. We would get the same thing if I had a rope here, and I just gave this a little jerk right here. I could send a little pulse down. This pulse would go down this wave. It would just act like a wave, and it would just transfer down the rope right there. Okay. Now, you'll notice here the disturbance was up and down. If I have a little piece of wood in here, this goes up and down as the wave goes off in that direction. Anytime the disturbance is perpendicular to the way the wave travels, we call that a transverse wave. So a particular one would be an ocean wave. An ocean wave right here is a transverse wave right there. This wave on the string going up and down, if I push this up and down, this would be a wave on a string right here. Light is actually a disturbance this way, and it goes off in that direction. So light is also a transverse wave, light right here. Now, the opposite of a transverse wave right here would be called a longitudinal wave. If I look at this long slinky right here, you'll notice that's a transverse wave right here. I'm jiggling it this way, the wave is moving off in that direction. But there's another type of wave, and that is like this right here. This would be called a longitudinal wave. So this one, it looks like it got really close and then further apart, and then really close and then further apart, and then really close. This was the longitudinal wave. If you looked at any part on here, we'd go back and forth in the same direction that the wave travels right here. Sound is like this. If you look at a speaker right here, what do you have? You have the speaker goes like this. It compresses the air, decompresses it, compresses it, and decompresses it. So you get this, you can't see this, but this is the compressed air and the decompressed air, compressed air, decompressed air. So sound is a longitudinal wave. Sound right there. Okay. Now, properties of waves right here. One of the properties of a wave is something we call the wavelength. The wavelength is the distance between one point and where it repeats itself. So it could be from here to here, or it could be from here to here. And so we call that the wavelength. The distance, say, from here to here, we call it the wavelength. And they usually use that symbol, like the Greek letter lambda, meaning, and that's, if these are ocean waves, that's so many meters right there. So the next time you're down at the ocean and you have a long tape measure, go out there and try to measure this wavelength. Now it's pretty difficult because it's moving on you. So it's a lot better if you have two people and slowly get different distances apart until they're both peaks are at the same spot, and then look at the tape measure right there. Okay, so that is the wavelength right there. Now we can also define the frequency. The frequency is how many waves go by every second. So maybe there's a pole sticking up in the ocean, or some pole sticking up. or it could just be a person out there, and just count how many waves goes by them every second. That's the frequency. So the frequency is the number of waves passing every second. So frequency is number of waves passing per second. Okay. And we usually give the symbol for that little fancy F right there. Okay, so it could be one wave passing every second, or two waves, or half a wave passing every second. And our one wave equation is, if you multiply these two together, that is, if we multiply the wavelength times the frequency, that gives you the speed of the wave. So this is the speed that this thing moves. There's the speed going down right there. So if you ever wanted to find the speed of ocean waves, measure this number, multiply them together, and that would give you the speed that the ocean wave is traveling right here. Okay, and usually all ocean waves travel at the same speed because it's usually dictated by the density of water, and the density of water is always the same right there. So this is the speed of the wave. Now, if it ever gets shallow, let's say the ground gets shallow right here, then there's friction on the bottom part. The top part still has inertia, so it's going to get out a little bit out in front of it. And eventually, when it gets shallow enough, it's just going to crash over because you're slowing down the bottom part of the wave and the top part keeps going right there. So that's why waves usually always crash at a certain depth. So if they crash way out there, let's say you're in Hawaii and they crash way out there, it means it's shallow way out there. Okay, so there is our wave equation. It works the same way with this. This would be the wavelength right here from here to here. And the frequency would be the how many of them go by every second right here. So now you know something about longitudinal and transverse waves. Let's come back to our wave on a string. Suppose we have a rope right here, and we come along here and we give it a little jerk right here, and we send the wave down the string right there. Now, what determines how fast that goes right there? What is the speed of that wave? I mean, I don't have a frequency and a wavelength. I'm just sending down one pulse right there. Well, if you look at this string right here, you'll notice right here, if I just give a jerk on it right here, this thing, wave heads down, it moves down. But you notice if I pull it a lot tighter, that's a heck of a lot faster right there. So the more I pull on this thing, the faster the wave travels. So actually, for a wave on a string, the speed, actually, it'll go faster if you pull the rope tighter. So it depends on the tension in the rope. And it also depends on the thickness of the rope. A real fat rope will go real slow. So it's in the bottom. I'm going to write TH for the thickness. So that's the thickness. And that's the tension, how tight it is, tension. And it just so happens that there's a square red in there. So now the units work out right here. This is the speed of a pulse down the rope right here. Now, as this pulse moves down, what does it do when it gets to the end of the rope right there? It can't just run off the rope because all that energy, this has energy, would just disappear. So what happens is when it gets down to the end, it actually bounces back. Exactly. So if I sent it down like this, when it got to the end, it would actually bounce back like that, right here. Now, let's say this one's on its way back, and I send another one down, and so now you've got this wave going this way, and you got another wave coming back. What happens when the two pass each other by? Well, the total wave is just the sum of the pieces. It's just the sum of this plus this. And if you add this plus this, you get one that's just twice as big. So as they pass, they get big, and then it's back to slowing down lower again right here. We call this interference. It's constructive because you're adding two positives. It just makes it bigger positive right here. Now, what would happen if I tied this end down right here? If I tied that end down and not let it come up right here. Now, when I send a pulse down, when this pulse gets to here, it's going to try to pull it up, but it can't because it's tied down. And so what's going to happen is this thing's going to flip over and come back the other way right here. It'll flip back upside down. So if you tie it down, it comes back upside down. If you don't tie it down, it comes right side up. And if I sent another one, when this one passed this one, you would be adding this wave plus this wave, and that gives you flatness. You would get anything right there. It would be flat for that one split second, then you'd get it again right here. We would call this destructive interference right there. Okay, so these are the two ways. Now, what would happen if I tied down both ends right here? If we tied down both ends, let's say I give it a little pluck. It's kind of like a guitar string right here. What are we going to get right here? Well, then we're going to get waves bouncing back and forth right here. Now, before I have them bounce back and forth, suppose we come back to here, we tie this end down, and I keep shaking this faster and faster right here. If I keep shaking it faster and faster, eventually I'm going to hit what's called a standing wave. And I'm going to get this wave to look like this. Right there. And we can see it with this slinky right here. Hopefully I can move it fast enough. So if I move it fast enough, right there. You see right there? It looks like that picture right there. Okay, and now if I shake it a little faster, it'll probably go crazy. And if I keep shaking it faster still, I'll get another standing wave that looks like this. Now I have to shake it twice as fast to get that. I don't know if I can shake it that fast, but let's just see if I can right here. So, yeah. I don't know if you're seeing it right there, but you would get something that looks like this. If I could shake it 3 times that fast, I'm never going to be able to do that. Then I would get something that looks like this, right? That is, I get these points, they're called nodes right here, and they should stay fixed if I can keep that up right here. Well, it just so happens that here I can shake this string using the 60 hertz in the wall. This string should shake 60 times a second, and if I adjust the tension just right, I get standing waves. So you can see right there, you see. All right. Yeah. Keeps. All right. There, you can kind of, I can't just move my hand here because whenever I change the tension, it affects it right there. But you can see right there. That's a good spot right there. You can see there was a node there and there was a node there. And so we got these standing waves. But I had to adjust the tension to get that. So I kept losing it. But if I tie them down at both ends and pluck it like a guitar string, then I always get the standing waves right here. Now you might ask, which one do you get in a guitar string? Which one of the standing waves do you get? Well, you get all of them. Actually, you have a guitar string. Next time you see a guitar string, go look at it really close. But there would be the standing wave right there. Then you'd also get this wave right here. It would be inside that wave, so it would be kind of like this right here. And then you'd get the third one right here, which would be and the fourth and the fifth and the sixth. This is what makes a guitar sound so good, because we would call this original one the fundamental frequency. Fundamental frequency. We would call this one the second harmonic, the third harmonic, the fourth, and this is twice the frequency, and this is 3 times the frequency. And when you put all these together, it sounds good right here. Now, suppose someone plays the guitar and they say, play middle C for me. Middle C has a frequency of 256 shakes per second, hertz. Well, which one are we talking about? The fundamental frequency, the second or the third harmonic? We're actually talking about this one up here, the fundamental. When they say play a certain frequency, they're actually saying play this. This is the dominant one right there. Okay, so now we know that the definition of the wavelength, this is one wavelength from here to here. It repeated itself. Here's one wavelength. This is only a half a wavelength. So the length of your guitar string for the fundamental frequency, that length, is half the wavelength. Or the wavelength is twice the length of your string. The wavelength is twice, I just moved the 2 over there. So there's the wavelength. Now if we come back to our wave equation, which says the frequency times the wavelength is the speed right here. Well, let's just solve for the frequency. That's the pitch you're playing, which is V over the wavelength. We said the speed is the square root of the tension over the thickness. So that's what the speed is. It's the square root of the tension over the thickness. And the wavelength, we said, was twice the length of the string. So 1 over twice the length of the string. So I could call this the guitar equation right here. This tells you the note you're going to play, and it depends on the length of the string, how tight the string is, and how fat the string is. That's all that matters right here. Now, when you're playing the guitar, you don't always play the same note. You play different frequencies all the time, so it sounds nice right here. What do you change when you're playing? Well, what do? You put your finger over the end right here, and you're changing the length of the strings. So what you're doing is you're changing L here by moving your hand. That changes the pitch right here, and that's what makes you apply different notes right there. Now, when you're tuning the instrument, you turn the little peg at the end, using the tension there to tune the instrument. If you wanted a bass, then you would take out the little strings and replace them with the big strings right there. And now you've got much lower frequencies right here. So we could call that the guitar equation right there. So, or we could even talk about the more popular instrument than the guitar, which is the jug right here. What's the jug? The jug is, you have a big jug right here. And then what do? You blow air over the top of it. They usually don't let you in the band if you're a jug blower. We'll see why right here. But you notice when you blow air over a jug right here, you are lowering the pressure. Remember, that was Bernoulli's principle. The pressure gets lowered. It sends a pressure wave down, it bounces off and comes back. So you keep sending pressure waves, and if you blow it just right, you can't just willy-nilly blow across this. If you could see the pressure, it would look like this right here. That is, the pressure is a minimum there. That would be a node, and here the pressure is quite great because it bounced off right there. And if you can get that standing wave going, then it gives off a tone right here. And you notice this is 1/4 the wavelength because it's half of that right there. So here, the length of your jug is 1/4 of the wavelength, or the wavelength is 4 times the length of your jug right there. Well, if we come back over here and plug it into here, we got the frequency times 4 times the length of your jug equals the speed. Well, the speed of what? Well, this is the speed of sound. right here. This is the speed of sound. That's what's bouncing up and down right here. So here we can get the frequency, we can get the Jug equation. The frequency of the Jug equation is the speed of sound divided by 4 times the length of your jug right here. So if you have a long jug, this is big, that's a low note right here. But on this, you don't get all the higher harmonics, so it doesn't sound like a guitar right here. You only get one note. And so if you want to make it sound good, you're going to need a lot of jug blowers right here to make it the sound nice right here. This is also a nice way to measure the speed of sound, because if you can get a tuning fork up there, you know the frequency, you know the length, and you can just dip this into water and you can get the length, and by multiplying this together, you can get the speed of sound. The speed of sound is around 340 meters per second right there. It depends on the temperature. When it gets a little hotter, it goes up a little bit right there. So, okay, so there's our jug playing right there. All instruments that are in an orchestra, they all have these higher harmonics, whether it's a horn or a violin or whatever it is, a piano, they all have these higher harmonics right there. So there is the Jug equation right there. Now, let's say we have our speaker, and we listen, there's my ear over here, and we hear a certain frequency coming out right here. There's a certain frequency coming out. So here's this sound wave. I'm going to draw them like transverse, but remember, they're really longitudinal waves. But now, let's say this speaker is now coming toward, it's on a cart and it's going towards you at a certain velocity. Well, what's that going to do to these waves? It's going to compress them right here, which means as this thing comes towards me, the wavelength gets smaller, the frequency gets bigger, and we call that the Doppler effect. So if a car is making noise and it's coming towards your ear, you hear a higher pitch. When the car moves away from you, you're stretching these waves out, you hear a lower pitch. You hear it on the racetrack. When the car goes by you, it's a high pitch, and then it follows and it's a low pitch right here. Again, that's all the Doppler effect. Well, this is what police use to detect whether you're speeding right here. Here you have a car, right? It's your car speeding. What they have is they have something that gives off a radio wave or a light wave. It doesn't matter. It gives off a wave. It could be even a sound wave, but they probably use a laser right here. But they send off a light wave right here. Now, if you're moving away from them, then this wave, since it's moving away from, the frequency coming back will be lower, or the wavelength will be longer, and so it'll be, longer. And all they have to do is know the frequency they're coming at you and the frequency that reflects back. From the difference, they can get your speed. Now, if you're coming towards them, the frequency back would be higher, and again, they take the difference, and that tells you the speed they're coming at them. If you're going perpendicular to them, it doesn't work right here. So you can do circles around them. They can't measure any of that speed. They can only measure the speed towards and away from you. This is the way we measure the speed of stars nearby, how fast they're coming at us or going away from us. If we look at the sun, if we look at one side of the sun, we see it coming at us. If we look at the other side, it's going away. We can get the rate of rotation of the sun right here. This is all called the Doppler effect right here. Now, so you notice here, when this thing makes sound right here, this speaker, let's just make it, here's my speaker right here, and it's making these sound waves. And when this thing moves forward, you're kind of compressing these waves and you're kind of stretching them out over here. But let's say you go faster than the sound right here. If these are sound waves, let's say you go faster than the speed of sound. Well, how can we do that? Say in a jet. Here we got some jet that's going this way faster than the speed of sound. Well, earlier, let's say when it emitted some sound, let's say the sound comes all the way out to here from the jet. but the jet's not here anymore. By the time the sound got out to here, isn't the jet out in front of it? He's going faster than his own sound right there. Matter of fact, if you look at all the previous sounds that were made previous to this, they're all behind it. And if you look at them all, they're all like this. They're all piled up behind you. And we can see from right here, all these waves are all on top of each other. And we already said now they just interfere to give you a big wave. So you get this big wave that follows the plane around, this big pressure difference right here. And if this goes by windows, it can break windows right here. That's why we don't go faster than the speed of sound around here. And this thing just follows the plane. It's like a cone that follows the plane. Once the plane slows down and this cone hits it, they're going to feel it in the plane right there. They would also feel it when they go from less than the speed of sound to greater. Now, we don't notice this too much with sound because we don't get in planes too much like this, but we do drive in boats that go faster than water waves. And you never notice if you've ever gone water skiing, if this is the boat looking straight down from up above, and the boat takes off, there's a big wave that goes off this way and this way right here. People like to water ski in these areas right here. And the faster the boat travels, the smaller this angle gets right here. This angle kind of narrows in. And matter of fact, if your speedometer breaks, and this is your boat right here, you can always just glue a little protractor on the back and then just measure that angle that this wave is, and from the size of that wave, you can get the speed of the boat right there. It's a cheap man's speedometer right there. So you can go faster than ocean waves. Ocean waves are quite slow. So now, can you go faster than the speed of light? And the answer is yes, you can go faster than the speed of light, but you can't go faster than the speed of light in a vacuum. When light hits the atmosphere, or when it goes into glass, or when it goes into a material, so if this is the Earth, and here's the Earth's atmosphere right there, when light hits the Earth's atmosphere, it slows down. It goes slower when it goes into material. Charged particles, protons, electrons, they don't slow down when they hit the atmosphere. And so these particles can be going faster than the light inside the air, not out here in vacuum of space, but they can in here. And what that does is it gives you a little flash of light on the surface of the Earth. Not enough for your eye to detect, but if you put sensitive equipment out there, you can detect these little flashes of light. It's just from charged particles going faster than the speed of light right here. They call that Cherenkov light right here. Sometimes in a nuclear reactor in the water, nuclear reactors give off fast particles that go faster than the speed of light in that water, and it glows right there. And again, it's called a Cherenkov light right there. So you can go faster than the speed of light in a material. Right here. Okay, so this is the Doppler effect. But now, if we just say something about sound right here, well, maybe we'll talk about sound on the next one right here. So this is just the waves, our guitar and our jug equation, and the Doppler effect. And we call this the sonic boom right here when you go faster right there. Okay, that's good.